In the first special symbol we examined is Kronecker delta. It's unit matrix, and it's useful in simplifying certain algebraic or differential equations in elasticity formulations. And the second symbol is related to cross product operation. That's called alternating symbol. Let's see the definition and certain properties of this symbol, second symbol. And the second one has three indices. It's epsilon ijk. Epsilon with two indices will be reserved for strain. But epsilon with three indices is not strain. It's a third order tensor, and it's called alternating tensor or alternating symbol. And since there are three indices, this has a total of 27 elements or entries. That is as isotropic tensor. We'll talk about transformation, but the entries are not changed when you apply coordinate transformation. And how do we define this mathematically? There are three subscripts, and if any of two are equal, this has to be zero. It's the first condition. It's a conditional tensor. If the values taken by ijk are unequal in cyclic order of 1, 2, 3. So if any of two are equal, 0. If they are unequal in this order, 1, 2, 3. So it could be 1, 2, 3, 3, 2, 3, 1, or 3, 1, 2. This is named cyclic order of 1, 2, 3, and this is 1. So this is, you can see that, related to cross product of unit vectors. For example, cross product of E1 and E2 is E3 plus, the plus, and E2 and E3 is E1 and plus. But if you change the order, and this is referred to as non-cyclic order of 1, 2, 3, or the reverse order. For example, 1, we are not moving in this direction, we are moving backwards. 1, 3, 2, 2, 1, 3, or 3, 2, 1. This is called non-cyclic order. In this case, this has to be minus 1. For example, E2 cross E1 is a non-cyclic order, it's equal to minus E3, and that takes care of the minus sign. That's a definition of alternating symbol, and we can use it in cross product to write cross product in index notation. It's useful. Cross product involved in different theorems, for example, in integral theorems, in definition of different types of vectors, curve of a function, for example. That's needed in many different applications. And cross product of two vectors, uj and vk, is epsilon is written as epsilon ijk uj vk. Now I'm having these vectors u sub j and v sub k. And in this order, to write down u cross v, you pre-multiply them by epsilon ijk, the alternating symbol. Now, the question is, how many entries do we have here in this definition? Again, this is a question for you. How many entries do we have in epsilon ijk uj vk. There are dummy indices here, right? And how many entries do we have here? You can answer this. What's the number of free indices? How many free indices do we have here? You know this, right?
One.
One free index. And then how many terms? If number of free indices is 1.
3 terms.
Yes, there are 3 terms. That's right. This should be a vector, and it's a vector because cross product of 2 vectors is another vector. And this is a vector with 3 subscripts I, j, and k are free indices. And show that this is indeed the cross product operation. I can evaluate terms one by one to show that this is cross product. This is the expansion. I is free index. Evaluate this for I equals 1, for example. Wi equals the new vector is epsilon ijk uj vk. And how do I evaluate this for I equals 1? I is equal to 1, and then I have a double summation over j and k. And how do we expand double summations? We assume we assign a certain number to j. For example, j can be 1. And carry out summation over k from 1 to 3. Then increase j, fix it as 2, again, summation over k, and finally, j is 3. So in line 1, j is 1. Line 2, j is 2. And line 3, j is 3. And in all terms, I is 1 because we are expanding this for I equals 1 now. This is only one of the terms. And in line 1, I'm expanding the summation over k. In explicit form, we have epsilon 1, 1, 1, u1, v1. We are fixing j as 1. This becomes epsilon 1, 1, 2, u1, v2, plus epsilon 1, 1, 3, u1, v3, summation over k. Increase j by 1, you get u2, v1 plus u2, v2 plus u2, v3. Increase j by 1, u3, v1, u3, v2, 3, v3. So v2 double summation. But this is simplified as per the properties of the alternating symbol. If any 2 of the indices are equal, that term is 0. So these dashed lines are over the terms that are 0. 1, 1, 1, 0. 1, 1, 2, 1, 1, 3, 1, 2, 1. All contains 2 equal terms. All of them are 0. This is non-zero, and this is non-zero. Epsilon 1, 2, 3 is 1. Epsilon 1, 3, 2 is minus 1. Result, in other words, is W1 equals U2 V3 minus U3 V2. So this is the first component of our cross product operation. You can repeat this for I equals 2 in a similar way. For I equals 2, expand the summation, a similar summation with different terms, and you'll find W2 as U3 V1 minus U1 V3. V3 is U1, V2 plus U2, V1. These are elements of cross-product operation. I can compare them. This is cross-product operation in matrix notation. U cross V is equal to this determinant. Regular cross products, the first row contains the unit vectors E1 hat, E2 hat, E3 hat. In the second row, we have scalar components of U. Third row, you know how to expand the determinants. Thus, U cross V is given in vector form. This is the vector form, and compare the elements. The first component of this vector, U2 V3 minus U3 V2. We get the same result from index notation. Second term, third term. Thus, whenever we need cross product operation, we have to refer to this notation or this presentation. And epsilon ijk can also, it will be needed whenever we have to evaluate moments, for example. We will derive equations of equilibrium for a solid body. And if you think about equilibrium equations, there are two main equilibrium equations. Total force or resultant force acting on a body has to be zero. And the second one is total moments about a point in space is zero. And moment means cross product of forces. So you have to introduce this tensor in your formulation. So in this course, we will deal with formulations, derivations, mathematical results in all sections. And of course, we will give examples and show the applications. And that's going to be an illustration of the use of cross-product operation. And this is the second special, this was the second special symbol, alternating symbol. Those are commonly used tensors in mathematical analysis. Kronecker delta, this is not Dirac delta, of course, it's a completely different definition, Dirac delta. This is unit matrix. And this is a third order tensor. It can be shown that they transform as a tensor, but first we need to know what we mean by transformation or coordinate transformation. And how do we do this for different orders of tensors? That's coordinate transformation. This figure is representative of coordinate transformation. We have an original coordinate system, x1, x2, x3. So x1, x's, x2, x's, and x3, x. This was our original coordinate system. These axes have the unit vectors e1 hat, e2 hat, and e3 hat. I can write a vector in this coordinate system. A vector is given here. It could be velocity in elastodynamics or displacement, force, or any other vector you can think of. And this can be written in the original coordinate system, xi. Now, what are the elements of this in the rotated coordinate system? So we apply an arbitrary rotation to the axis, and a new coordinate system is generated. So x1 prime, x2 prime, and x3 prime. The unit vectors are primed. What are the elements in these coordinate systems, or what are the elements of V in the new coordinate system? It's not too difficult to find this. It requires some result from statics. First, we define a direction cosine matrix, Aij. These are cosines of the angles between xi and xj prime. And this is mathematical representation of this definition. Aij is a direction cosine. It's therefore the cosine of the angle between xi and xj prime, x1 and x1 prime. The angle is given. Suppose it's given. Its cosine is a11. And all of them, all 9 of them can be defined in this way. Now, how can I express this vector v? In the original coordinate system, v is v1, e1, v2, e2 plus v3, e3. These are the scalar components of v, v1, v2, v3. In a new coordinate system, primed coordinate system, the components are different. So v1 prime, e1 prime plus v2 prime, e2 prime, v3 prime, v3 prime. Two different ways of writing the same vector, but I can express unit vectors, a unit vector, for example, e1 hat, in the primed coordinate system, because from statics, I know that components of a unit vector are direction cosines. I'll review this information from statics if necessary. For example, E1 hat, unit vector in the primed coordinate system. It has 3 components. And the first component is A11, direction cosine for x1 and x1 prime. It's A11. The second component is A12, E2 prime hat, and the third one is A13, E3 prime hat. A unit vector can be written in a coordinate system. Its components are direction cosines of that unit vector in the considered coordinate system. E1 hat can be written in terms of EI prime hat. And you can introduce these direction cosines for E2 hat. E2 hat in the primed coordinate system is direction cosine times sum of direction cosine times the corresponding unit vector. So now direction cosine between 2 and 1, 2 and 2 and 2 and 3. There's the second row of our matrix Aij. And this is the second order tensor or a matrix, and we will refer to this as transformation matrix. And the third one is written in a similar way, E3 hat. And now, using this representation from vector algebra or statics, I'm able to find the result because I can substitute these E1, E2, and E3 into this representation. You see, substitute this expression here, second line, this term, third one here, and you'll be able to express the same vector in terms of primed quantities. This is V1A1 plus V2A2 plus V3A3, but we know what E1 is in terms of primed quantities. This is E2, this is E3. The same vector written in the no coordinate system, and this should be prime. You can place a superscript prime here to indicate that this is the prime, but we can simplify this, factor out E1 prime here, factor out E2 prime, and factor out E3 prime, and you will get a compact equation. That is, if you factor them out, do I have this? No, I don't have. You'll be able to write this as V1 prime, E1 prime heads plus V2 prime, E2 prime head plus V3 prime, E3 prime head. And what is V1 prime? A11 V1 plus A21 V2 plus A31 V3. This is the scalar component in the new coordinate system. The second term is A12 V1 plus A22 V2 plus A32 V3. Second term is V3 prime. This is V2 prime and V3 prime. Therefore, V is V1 prime, V1 prime, V2 prime, 2 prime plus 3 prime, 3 prime. And each component is found. It's called coordinate transformation for this vector. And why did we introduce index notation at the outset? To simplify this representation. We don't need to write all equations all the time. You can show this vector transformation as a single equation in index notation. I can express this as a single equation. And this equation, if I assume that the subscript is j here, vj prime, I have a summation, right? 1, 1, 2, 2, 3, 3. So this should act as a dummy index. And that dummy index is I here. The second subscript is fixed and equal to this subscript. So this j is same as the j on the other side. Therefore, there is a summation here, and vj prime here is equal to aij vi for ij equals 1, 2, 3. You see that j varies from 1 to 3. J equals 1, j equals 2, j equals 3. And in each equation, for each j, I varies from 1 to 3, hence the summation. This is the main vector transformation formula in tensor algebra. It's the main result. It's applied transformations of all vectors, of course. And we will frequently refer to this result in our computations. How do we express vector transformation using index notation? And it is useful to represent it in matrix notation as well. If you think about this and define at this point a transformation matrix A. Aij is transformation matrix, as I mentioned. These are the elements of Aij. After this transformation matrix, we are multiplying this bit by V, but not the matrix itself. As you see, this goes like 1, 1, 2, 1, 3, 1, 1, 1, 2, 1, 3, 1. We are actually multiplying the transpose of this matrix with V. Thus, this is our matrix notation of the same equation. V prime equals A transpose times V. Again, a coordinate transformation formula. In matrix notation or in index notation, you need both forms. And a vector, if you have a quantity comprising 3 entries, it can be defined as a vector only if it obeys this transformation formula. You cannot arbitrarily define any quantity with 3 numbers as a vector, but if it transforms according to this formula, such as displacement vector, or any force vector, or any other vector, they all obey this transformation formula. Thus, this is a first order tensor, A vector is a first order tensor. And some features on transformation matrix. A times A transpose is identity matrix. And therefore A transpose times A should be equal to A times A transpose, because A transpose is A inverse. So this could be a check on your computations. You may check whether the matrix is orthogonal or not. A is referred to as an orthogonal matrix. Always A transpose should be equal to A inverse for transformation matrices. And I can find the inverse formula here. Suppose that I want to write this original components in terms of primes components, or I want to write V in terms of V prime. And note that the matrix is constructed in such a way that this column is X, the original system, and the row is prime. Pre-multiply each side by A. A times A transpose becomes identity matrix. Identity matrix times V becomes V. So V is equal to A times V prime. That's the second result. In this definition, V is A times V prime. The same set of equations can be written in index notation as well. That is, V in terms of V prime in index notation, we have a similar presentation, but order of subscripts are interchanged, because this is A and the previous one was A transpose. Vi is Aij Vj prime. Another way of expressing vector transformation. These are transformation formula in summary for first order tensors or vectors. They are now derived by considering elements from statics, and they are known, and you can apply them to carry out coordinate transformation for first order tensors. Any questions about these results or this part in general? Any questions or comments? This was first order tensor, which means that we have different formula for higher order tensors. You can develop a transformation formula for second order tensor, for example. And it's going to be our main result for stress transformation. Because as we will see, or as you already know, stress is not a vector. I mean, stress at a point. And traction on a surface is also stress, but we are talking about stress at a point. And it's a second order tensor. An extension of this result is used. You insert another matrix here. And number of matrices is equal to the order of tensor. If you have transformation for a third order tensor, you have three tensor multiplications, mathematics multiplications. In that case, it's getting somewhat more complicated, but straightforward from a programming point of view. And these are short and compact useful notations we need in our computations and derivations. If you don't have any questions, I'm going to end the lecture at this point, and we will meet next time.